Aircraft are pressurized when we fly at high altitudes to trick our bodies into thinking we're much lower down. But how do we do that? Let's find out. Hi, I'm Grant and welcome to the 16th class in the AGK series. Today we're going to be taking a look at air conditioning and pressurization. Pressurization is essential for high altitude flight because humans can't survive for very long up at high altitudes, and we need to trick our bodies into thinking we're a lot lower down than we really are. The way that we do this is through the air conditioning system. So today we're going to have a quick look at both of these systems, so hopefully you understand them in time for the exam. The main driving force behind the air conditioning and pressurization system is the pneumatic system. I debated whether I should give the pneumatic system its own separate video, but decided a quick summary at the start of this video would be sufficient. The pneumatic system uses compressed air to drive things. There's a long list of things such as the air conditioning and pressurization systems, but also, depending on the aircraft, things like anti-icing, instrumentation on some aircraft, thrust reversers, secondary flight controls, air-based engine starting, and to add pressurization to systems like the hydraulic system and the reservoirs within that system. So it's a weird one because you could argue that all those systems I just listed are part of the pneumatic system, but I see the pneumatic system as just a source of power for these systems, just like electricity or hydraulics could be other power sources. The main advantage of using pneumatics is that there's a lot of air around us and we don't need to carry tanks of air around with us. We just suck up air from all around the aircraft. We can then compress it to add pressure, which we can then use to move various components like valves and actuators. The downside of using air to move valves and actuators is that air is compressible. Therefore, if we wanted an immediate input, there would be a slight delay as the gas compresses before we can then move the component. This is why pneumatics aren't used for precise, rapid control inputs. Another problem is that leaks can be very hard to detect because air is obviously odorless and colourless. So with big essential components like the landing gear, we use hydraulics so we can easily see leaks during a walk around and get them repaired before we leave the departure gate. To get the compressed air, we just take it from an electrical compressor attached to a piston engine, essentially a pump that forces air through it and squeezes it together before it is then used by the aircraft. Or in a jet-powered aircraft, we already have a compressor of air in the engine. The engine squeezes air for us, so we take some of that air before it gets mixed with the fuel and ignite it, and we use that air for the air conditioning and pressurization and all the other systems after we cool it down a bit. We call this type of pneumatic power bleed air. This draws air away from flowing through the engine, and if you've watched the jet engine videos in this series, you will know that the power generated by the engine is proportional to how much air is flowing through the engine. So by bleeding air for pneumatic use, we actually degrade the performance of the engine. And that's pretty much it for the pneumatic system. But as I said, a lot of things use this as the power source, and one of those things is the air conditioning. Air conditioning is essential because the environment at 30,000 feet or more is not nice. It's about minus 45 degrees Celsius and the air is much lower pressure, whereby we will pass out if we even breathe it for a short period of time due to lack of oxygen absorption by our lungs. So we want to have some warmer air and we want to pressurize the aircraft so that our lungs think we are at a much lower altitude and can absorb all that tasty oxygen. Air conditioning and pressurization are linked very closely and they both rely on each other to function. Today we're going to have a look at air conditioning first though. In a jet, the basic overview is that we take bleed air from the engine and cool it down, then add it into the cabin and cockpit to heat up the ambient air. We use bleed air because it's already hot and it's more efficient to cool down hot air than it is to heat up the cold air outside the plane. And we can cool down that air in a few different ways. The first way we can do this is we can put the air near something colder. The colder surface draws away heat from the hot air and cools that hot air down. This is how fans in a computer work. The hot surface has cold air passing over it, and the cool air draws away the heat which cools the component down. We can also make the air expand, which drops the pressure and the temperature. The combined gas law says that P1 V1 over T1 equals P2 V2 over T2. So if we just add some numbers to that, we can see the sort of thing that will happen. So if we say in this left-hand side that we've got 10 times 10 over 10, which is going to equal 100 divided by 10, which is 10, okay? On the next side of the equation, we're going to say that once we've expanded the air, we're going to have a volume which is twice as big. So that's 20. The pressure and the temperature both drop, but they don't drop in the same amounts. So if we add some figures, something like that, we can see that this also equals 10 on the right-hand side of the equation. So by expanding the volume, we get a pressure drop and a temperature drop. And it's important to know that these numbers are completely inaccurate. It's just to show that the increase in volume will cause the temperature and the pressure to drop because of the combined gas law. The final thing we can do is we can make the air exert some of its energy onto something, or basically do work. It's thermodynamics, and it's a bit unnecessary for this class and this course in general, but in essence, the molecules in the air are moving around rapidly with lots of kinetic energy, and this is what we perceive as heat. Then the air uses some of that kinetic energy to do work, like push a component, for example, and this results in the molecules moving around a bit less because the component that is being moved took some of the kinetic energy out of the air for its own use. And due to these molecules moving around less, they generate less heat, and aka, by using energy from the air to move a component, we have caused the temperature of that air to drop. Packs are at the heart of the air conditioning system. They stand for Pressurization and Air Conditioning Kits. These components take bleed air and reduce its temperature and pressure to suitable levels. This is a diagram of how they work, and they are controlled by a computer that senses what temperature output is desired, and then it will open and close valves accordingly. It looks complicated, but it's not quite as tricky as it looks. So the first thing that happens is air comes in here through a flow control valve, and then the flow of the bleed air is split into two. Some of the air passes through the first heat exchanger using that first method that we just saw in the previous page. In this heat exchanger, the pipes containing the hot bleed air have ram air passing over them. Ram air is just another word for external air. This cools down the bleed air in the pipes, and the other stream of air bypasses the heat exchanger, and by controlling the amount that bypasses, we can control the temperature of the air at the entry into this next bit, which is called the air cycle machine, which is also sometimes known as the bootstrap system. This system basically containing the compressor and the turbine. The first part of the air cycle machine is a compressor, so we slightly increase the pressure and temperature of the processed air. We then pass the processed air through a secondary heat exchange that works much like the first one. Then the air passes over a turbine. This takes advantage of the air exerting energy to cool the air a bit further. The function of the compressor is to ensure that the correct pressure of air is delivered to the turbine. This is because the turbine will be designed to operate at a certain pressure. So by controlling the amount of processed air and unprocessed air entering the air cycle machine through this bypass valve here, we can then control the pressure that arrives at the turbine. At the output of the air cycle machine, there is a device used to take out the ice and water to control the humidity of the air. This fully processed air is then mixed back in with some original unprocessed bleed air to control the output temperature of the pack. So we have 2 points where we mix the cold and hot air streams, if you like. One to ensure the correct temperature and pressure for the air cycle machine and the turbine, and then one to ensure the requested output temperature of the pack. It might need no additional hot air, or it might need lots. That's where the computer controlling the pack comes into its own, and it opens and closes all these valves as needed to deliver the correct pressure and temperature to the turbine, and then the correct temperature and pressure in the output phase of the pack. Every aircraft has a different arrangement of ducts to distribute the conditioned air from the packs. Generally though, we have the outputs from the packs and an emergency ram air source and recirculation fans feeding into a central hub called a mixing unit. In normal flight, the recirculation fans suck up air from the cabin, not all of it, just some. This is then mixed with fresher, cool air from the packs, and the ratios of cool air to recycled air are controlled by cabin zone temperature controllers, which are computers that sense the temperature in the cabin, and they then adjust the amount of conditioned air added to the mixing unit as well as the amount of air that is being recycled. If we want different temperatures in each part of the cabin, then we can select and request on the control panel that temperature, and the mixing unit and zone controllers will always set the coldest desired temperature for all three of those units. So if this one's set 18, 20, and 22, they'll request a temperature of 18 degrees. This is because we can add heat back into the system through some hot air directly from the bleed source downstream of the mixing unit and before it even enters the packs. This is called trim air. The combination of the common mixing unit and then adding temperature back in later per cabin zone through the trim air is better than having a separate mixing unit per zone. This is because it basically means fewer ducts overall for the aircraft, for the pack outputs, and it also distributes and circulates all the air in the cabin, which is good for hygiene reasons. If you think about if the cockpit had a virus or like a flu bug going around, then it was always cycling in that one zone. It's better if it's cycling throughout all the zones in a way because it's diluted down a bit more. It's a bit of an odd one, but it just makes more sense. You've got a much larger area for the bug or virus to be spread out throughout, and it just means that you're less susceptible to get one of these bugs or viruses. To control the pressurization of the aircraft, we essentially let a bit of the air-conditioned air out or hold on to it so that we reach the desired cabin pressure. Think of it like letting a bit of air out of a balloon so it doesn't burst when you've blown it up too much. Now imagine that balloon but with two holes in our balloon, and someone is constantly blowing it up through one. In order for the balloon to not burst, we'd have to start letting a bit of air out of the other and regulate how much air goes in and how much air goes out to stop this balloon, or in our case, an aircraft, from bursting. The point at which the balloon bursts is when the differential pressure between the inside and the outside of the balloon gets beyond a certain limit. In an aircraft, we have a maximum differential pressure, usually equal to about 8 or 9 psi, somewhere in that range, before the fuselage starts to get damaged. This will normally be equated to a maximum operating altitude with a little bit of wiggle room so that we don't get right up to the maximum differential pressure. If we do get close to that maximum differential pressure, then safety valves will open up to release the pressure buildup and stop the aircraft exceeding the structural limit of the fuselage. The main component of the pressurization system is the outflow valve. We have a constant input into the cabin through the packs and air conditioning system. So our balloon, if you like, is constantly being blown up. Therefore, by controlling the output valve, we can control how much we deflate the balloon and how much air we release into the atmosphere, which keeps the cabin at a lower altitude than the air outside the fuselage and within the differential pressure limits. A computer known as a cabin pressure controller will automatically adjust the outflow valve to achieve a certain altitude within the cabin that humans can live and function in effectively. On the ground, the valve will be completely open with the pressure inside and outside of the plane being equal. But if we took off and kept the valve fully open, then the aircraft rate of climb and the cabin rate of climb would be the same. And that would be very quick, which is very painful and uncomfortable on your ears and sinuses and things like that. So the cabin pressure controller will command the outflow valve to close. This holds the cabin pressure at ground level. Then as we climb, it opens at a defined rate to keep the cabin rate of climb lower than the aircraft. Once the cabin is at the desired cabin altitude, the valve closes to hold that level. If we continue to climb in the atmosphere higher than the desired cabin altitude, aka the internal and external altitudes are different, then the valve will open again to allow pressure to be released and maintain the cabin altitude and differential pressure at desired levels. In the cruise, the valve will open and close to hold the cabin altitude and differential pressure at acceptable levels, and then in the descent, the valve will close when the cabin altitude and external altitude match, and then slowly open to lower the cabin altitude slower than the aircraft's rate of descent, again to help with the comfort in your ears and nose and things like that when climbing and descending fast. On landing, the valve will fully open to equalize the pressure between the inside and the outside of the aircraft. That is a very simplified version of how the valve operates. There are constant adjustments made by the cabin pressurization controller, opening and closing the valve to control the differential pressure and to keep the desired rates of cabin climb and cabin descent. Every aircraft will have a different sequence of when the valve starts to close and open and what altitude things happen, but that is just the general idea. If the cabin pressure controller computer fails, then a manual override will exist to allow the pilots to manually control the movement of the outflow valve through a dedicated actuator and motor. And by using careful monitoring of all the flight deck indications, you can achieve a reasonable rate of climb or descent and keep the differential pressure within the limits. So in summary then, the air conditioning and pressurization system are sort of two sides of the same coin, but they're driven by the pneumatic system. Pneumatic system powers a whole bunch of things on the aircraft, including the air conditioning pressurization, as well as anti-ice pressurization for the hydraulic reservoirs, sometimes some instruments and some secondary flight controls. And the way that we get the pneumatic air is through either an electrical compressor on a piston engine, or we can use the compressor already in a jet engine, and we can bleed air off of the engine, which reduces the power of the engine, but it does mean that we get some nice tasty pneumatic air for use in other things. Once we've got that pneumatic air, we need to cool it down. And there's three main methods we can do that. First of all, we pass cold air over the hot air. We don't mix it, we just keep the cold flowing over the pipe that the hot air is in, and this gradually cools down the air. We can expand the air. By expanding the volume of the air, we must reduce the pressure and the temperature to make this equation work. And then we can also exert energy. The particles are moving around really fast with lots of energy. We use some of that energy to move a component or something like that, and then the particles are moving around less with less energy, and that means that the heat is lower. The packs are the main driving force behind the air conditioning system. They basically take bleed air, pass it through a heat exchanger, and then into this system here, which is the bootstrap system or the air cycle machine, consisting of a compressor and a turbine. The compressor compresses the air, which raises the pressure and temperature a bit. And the whole idea of the compressor is that it delivers the correct pressure of air to the turbine, because a turbine is a combination of this effect and this effect. We're exerting energy and we're expanding the air. So this cools down the air a lot, and we want to deliver the correct pressure of air that the turbine is designed for to get the maximum cooling effect. That cold air can then be mixed in with completely unprocessed bleed air to deliver the desired output temperature of the pack. Once we have the air from the packs, we mix it in a mixer unit, which combines the air from the packs and recirculated air to achieve the desired cabin temperature. The cabin temperature controller, or another name for a cabin temperature computer, will always select the output of the mixer unit to be the lowest possible temperature that is requested. So again, 18, 20, 25, this is going to output 18 degrees for the cockpit. The reason we do this is because we can then add in hot air to achieve the temperatures of 20 and 22 degrees by using what is called trim air. This is basically if we took a pipe from the bleed air and bypassed this whole pack and went all the way into after the mixing unit, we can add in a little bit of air to bring the temperature back up for each zone in the aircraft. Pressurization is controlled by a cabin pressure controller, which is a computer that mainly operates this outflow valve at the back of the aircraft. We've got air coming in, we need to let some of that air out so that the differential pressure of the aircraft doesn't get too high and cause damage to the structure. And through opening and closing this valve, we can control the rate of cabin climb, the level that the cabin climbs to, because it's going to be different from the external altitude that we're actually climbing to, and we can also control the rate of descent of the cabin. We want a slower, more gradual rate of climb and descent because it's good for the sinuses, the nose, the ears, that kind of thing. And we also want a lower cabin altitude in general because humans can't survive at 30,000 feet for very long because there's not enough oxygen absorption by the lungs. And that's pretty much it.